Okay, this is a review of the review for the two-dimensional motion test. We'll just go through it one question at a time. We've got some new software here, so it might be a little bit clunky, but hopefully I'll get better as we go. Okay, so question number 1, and actually questions 1 through 7 examine the motion of just an ordinary object going in a projectile motion, and question 1 asks us about the velocity at point C. Well, the important thing to recognize at point C is that the velocity is not just any velocity, but it's pure x velocity. And we know that since there's nothing accelerating you in the x direction, that x velocity stays the same always. There's nothing to cause it to change. There's no gravity working sideways. So we can figure Vx at any one of these spots. And the easiest spot is at the very beginning, where we know the full velocity is 70, and we know the angle is 30. And so we can calculate Vx right at the very beginning as V cos 30, or 70 cos 30, which is equal to a little bit more than 60. I think it's 60.6 meters per second. And since that's the velocity Vx there, that's the velocity in the x direction everywhere, including at the top. Question 2 asks you to calculate the acceleration at point C. Well, the acceleration at point C is the same as the acceleration at all the other points there, because the thing that's causing this object to accelerate is none other than gravity, and gravity pulls down equally hard at every single location. Gravity does not discriminate based on where you are on the flight. And so at point C, gravity is what it is everywhere else. It is 9.8 meters per second squared, but pointing down, so negative. On question 3, we're asked to find the y component of the velocity at point C, and as we discussed earlier, there is no y component. It's pure x at point C, so Vy equals 0. Okay, our next set of questions, oh no, we're still on the same group here. Let's take a look at the pictures that I ask you to draw. And here we're wanting to look at the velocity vector and the acceleration vector at various points. So let's take a look at the first two panels. Oops, I just changed my pencil type. Hold on. Okay, here we go. Stand by. That's what I was talking about the new software. Okay, so in the first panel, our velocity is at its maximum. It's the full 70, and it's pointed tangent to the path. So if we're going to draw the path there, it would have been like that. We don't need to do that. So that vector there would represent the velocity, tangent to the paths, and the acceleration, of course, is straight down, equaling 9.8. And the next location at point B, here the velocity is tipped down a little bit, still tangent to the path, but not quite as upright as this one, and a bit shorter. Not quite as long because we've lost some Vy. Still the exact same amount of Vx, but Vy has shrunk, and our acceleration is still negative 9.8 straight down, and so on. For question number 5, we're asked to compare some velocities at different spots. First, let's examine the first one. It asks, how does Vy at B compare with Vy at D? Are they equal? And the answer is they are not equal, because at B it is going up. That's a positive number. And at D, the y velocity is going down. That's a negative number. And a positive thing cannot equal a negative thing. So the first statement is false. The next statement we would look at maybe is this one that looks at the vector, the full velocity at b. Well, that's this thing up here. This is the full velocity at b. Is that vector equal in all respects to the full velocity at d? If we looked at that picture up above, you could see that it's not. It's the exact same length, but it's a different direction. And if it's a vector equation, the length and the direction have to be the same, but these are not the same because the direction is different, therefore that is false. So the last one presumably is true. Let's take a look at it. We're saying that Vy at b is equal to negative Vy at d. That is true because Vy at b is exactly that long. Let's say Vy at d is that long, but if we put a minus sign in front of it, that means we're taking what was a negative number and turning it into a positive number, because a negative is equal to a positive. And these are indeed equal, and this one is true. Okay. Question number 6 asks us to figure out about how much time it was in the air going from beginning to end. So we're looking at the full flight. So let's figure that out. And we're going to need to use a y equation to help us to let gravity be our timer. If we look at our starting y velocity, it is 35, because remember Vy initial equals 70 sine 30, and that equals 35. And our final y velocity is negative 35. And so we can use actually either of the two y equations that have time in them. Here I will use the one that is the middle, the first y equation, Vy final equals at plus Vy initial. So our final over here is minus 35. Our initial to start with is plus 35. Our a is minus 9.8, and our t is what we're solving for. And so we can solve that equation easily for t. I'll subtract 35 from both sides. Minus 35, minus 35. That takes me to minus 70 equals minus 9.8 t. Divide both sides by negative 9.8. And we find out that t should be equal to about, what is it? It's about 7.1-ish seconds. For question 7, same event, but this time we're looking at how far it travels in the x direction. We'll keep the 7.1 seconds, but this time we're going to describe the event from an x perspective. Our initial x distance is 0, and our final x distance is what we're seeking. That's what we want. So let's use the only equation we have. X final equals Vxt plus x initial. Our Vx we determined from all the way back at question 1 was, I think, 60.6 or thereabouts. And our time in the air we just determined in question number 6, this is question 7, was 7.1 seconds. So we can put that time in, taking it from the y equation, putting it into the x equation. Remember, it's the only thing from the y equation that we can put into the x equation. And if we substitute that in, we can get our answer, whatever that is. Okay, let's take a look at the next question. This is number 8. In question number 8, we're being asked to add some vectors together. This goes back a little ways, but you remember you want to add vectors tip to tail. So let's do that. question number 8. Tip to tail, we've got 6 plus a 9 plus an 8. Notice that all those guys are tip to tail, so we've added here, and now our resultant is the shortcut from the beginning of the first to the end of the last. So we want to know if the magnitude of that. Since it's apparently a right angle, we can Pythagoras these guys. So that's 8 squared plus, well, how much do we have in the, let's see, 6 and 9, that's 15. So that's 8 squared plus 15 squared equals c squared. This is our unknown vector c. So 64 is 8 squared, 15 squared is 225. Add those two guys together and we get, what is that, 289 is equal to c squared. Square root both sides. And we get 17 is equal to c. So this is 17. And then what about the angle of this guy? 17 what? 17 meters per second squared, I guess, because everything else was. What about the angle? So what is that angle? Well, that's a first quadrant vector. It's pointing in the first quadrant. It looks like it's less than 45. We can put a little coordinate system at its tail. We're seeking that angle. And remember, that angle we can calculate by the inverse tangent of the y part divided by the x part. So that's the inverse tangent of the y part, which is positive 8, going in the positive y direction. And the x part is positive 15. And if you inverse tangent that with your calculator in degree mode, you should get the direction of this vector. That's question number 8. Okay, let's move on to question number 9, another vector question, and here we're looking at a single vector that we're trying to break up into components. It's a second quadrant vector because it's pointed off in this direction. Whoops, pointed off in this direction. Can I control Z that? Yeah, it looks like maybe. Oh, I'm in trouble. Stand by. Okay, let's get back to where we were anyway. I got to switch my pencil type again. There we go. Okay, so we've got a vector that is 20 meters per second long. It is at an angle of 120 degrees. And it's our job to figure out the components of this vector. What are they? Well, if we call this thing vector A, AX should equal A cos 120, and AY should equal A sine 120. And A is 20, so we can put that in there. And if you use the 120, that will work out just fine. You should get some negative value for the AX. Looks like it's going to be about negative 10 or so, just by putting in 20 cos 120. And AY should be a positive value because that's pointing upward. And so that should give you your answer on question number 9. Let's move on to question number 10. Question number 10. Okay, in question number 10, we've got it's a two-dimensional motion problem. We got a ball traveling at 15 meters per second. It goes off of a small cliff, 2 meters high, and the objective is to figure out where it hits. Standard sort of problem, because you want to break it up into the x and y motion. We'll use the y motion to help us figure out about the time. We got some dogs fighting in the background, so sorry about that. Sorry about that extra noise. Hopefully they stop soon. Okay, so in the y direction, we can try this equation. Oh gosh. I'm going to shut up those dogs. Stand by. Okay, so got the dogs put away. Our final, let's put our origin up here. That makes our initial y velocity equal to 0. Our final sorry, did I say velocity? Our initial y position is 0. Our final y position is -2. 1/2 of our gravity is -4.9 t squared. And the key thing here is now our initial velocity in the y direction, and notice that this is pure x velocity, no y velocity at all. And so we have this whole term here will be 0. There is no velocity in the y direction. So we're going to solve this equation for t, bring it over to the x world, and in the x world, what do we have? We've got x final. That's what we're trying to figure out, is our final x position is equal to v in the x direction, which is 15, because that's pure x motion times the time that we just solved for over here. 15 times whatever time you get should land you in just the right spot. Okay, we have just returned back to our question about the questions 1 through 7 and that initial launch. We're going back one more time and we're trying to determine how high point C is. So there's a few different ways to do it. One is, so we're on question 11. One is we can recall that we figured out that the total time in the air was equal to about 7.1 seconds. So that was from here to here. If we wanted to figure out the time just to the top, that would be half of that 7.1. So we could divide that by 2 and get something like 3.55 seconds or something like that. And then we could use that time in one of the y equations to determine the height. Maybe this one, 1/2 at squared plus v initial in the y, t plus y initial. If we choose our coordinate system to start right there, then our initial y is 0. Our initial velocity in the y direction we previously determined was a positive 35. Negative 9.8 for gravity. And then t squared, we can put in that 3.55 in both of these locations. Don't forget to square it here. And that should give you the highest value. Alternatively, we could have done this whole problem without any use of time at all, by going to the fourth y equation, the last y equation, v final squared equals v initial squared plus 2a y final minus y initial. And on that equation, our final velocity in the y direction up here is 0. Remember, we've got no y velocity at the top. So that means this whole term is 0. 0 equals our y initial velocity 35 squared plus 2 times negative 9.8 times our y final, because y initial is 0. And then we put a minus 35 on this side of the equation, bring that over, equals negative 19.6, 2 times 9.8, negative 19.6 yf. Divide both sides by negative 19.6. And there's our yf. That'll get us there as well. Don't forget the square on that 35, like I almost did. Okay, question 12a. What is the name given to the type of acceleration associated with circular motion? That's not centrifugal, but it's centripetal. Remember that petal means seeking toward the center. Centri, toward the center. Center, seeking acceleration. So centripetal acceleration is associated with circular motion. Many people in the rest of the world say centrifugal acceleration. You'll see that for the rest of your life, and this is not correct. Totally false. Doesn't exist. For reasons we'll understand pretty soon. Okay, next question, number 12b, was what is the direction? Well, if it's center seeking, what is the direction of center seeking? The direction is toward the center. So that's questions 12a and 12b. Okay, moving along, flipping the page. Almost done. We're now down to the Australian hunter who wishes to tangle up the kangaroo with her bolo. So our first question that we're trying to figure out is, what is the velocity of the bolo stone while it is being twirled? So here we've got the thing, it's going around. We're trying to figure out the velocity as it's being twirled. So what do we know? Well, we know that velocity in general is equal to a distance divided by a time. But the distances and times must correspond to each other. So we have to choose something that matches. So let's see. We know that it travels 3 revolutions per 1 second. So the distance is 3 revolutions. A revolution means that you have traveled all the way around the whole thing. You've traveled from here all the way around. So a revolution is a circumference. So 3 revolutions are 3 circumferences, 3 2 pi r's, because 1 circumference is 2 pi r of a circle. And the time, they said it was 3 revolutions per 1 second. So that's our velocity. And do we know r? Let's see. Yes, we do. It's 1.2. So if we put a 1.2 in here, we've got our velocity. Bingo. It'll be, what is that, 6 times pi times 1.2 all over 1. That's going to be, well, you've got a range there between 20 and 30 meters per second. Okay. Now we know the velocity. By the way, this velocity, while it's spinning around, is the same as the velocity it has the moment it pops off, which presumably is pure x velocity, since they say that it was I'm a little ahead of myself, since they say it came off in a horizontal way. But the next thing we're figuring out is the acceleration of the stone. So this was 13a. Let's take a look at 13b. 13b. What's the acceleration? Acceleration is v squared over r. Well, we've got v, we've got r, so you know what to do there. Let's move on. In the next part, we're trying to figure out, in 13c, we're trying to figure out how long it will be in the air. So like I was saying, it comes off horizontally. Stand by. Comes off horizontally. We already know the speed. We've calculated that, and that's pure x speed. We're trying to figure out how long it's going to be in the air. That's the timing mechanism is going to be gravity again. How far does it fall? 2 meters. So we're going to figure out the time in the air by using a y equation. So for our y equation, we'll use the standard equation here. Let's break this up into x and y thinking. In the y direction, we can say y final equals 1/2 at squared plus v initial in the y direction times time plus y initial. If we set our coordinate system, we can do it anywhere, but we'll do it at the release. So we'll call this our xy up here, origin. And so our initial y will be 0, our final y will be below that, 2 meters below that. And that will equal 1/2 times -9.8 times t squared. This term, you should know by now, goes away because it's pure Vx to start with. Okay, solve this for t, bring it, and that'll be the answer to question C. And then for question D, we can figure out how far away it is by using an x equation. X final equals v. What v? That v that we've already calculated in part A, plus x initial, which is 0. Okay. So we've got our v, we've got our t, put them in, and you should have your answer. And our final problem, this is one that we did in class already. And in this problem, we're trying to figure out the acceleration of this Ecuadorian who's spinning around pretty fast. To figure out his speed, we can look at the distance he travels in a corresponding amount of time. The distance is the circumference of the Earth, 2 times pi times, well, I give you the r in the problem so you know how big the radius of the Earth is. The time to spin around the Earth is 24 hours, one rotation, but we can't use it as hours. We have to do a little work off to the side and change 24 hours into seconds, and we know that 1 hour is equal to 3,600 seconds. So that's the number you want to put in there. Once we have that, that's our v, square it, divide by that very same radius that you used over here, and that should give you a number. We did this in class. That's right in the range given. And that should prepare you all for the exam tomorrow. If you would like a little bunch of extra credit, on your review, write your first name, your middle name, and your last name, and then I will know that you have watched this review in its entirety, and I will give you a bonus on your bonus. Good luck tomorrow. I wish you the best.